All right, good afternoon, guys. This is everything we need to know about nuclear chemistry for the review and for the final. So, first part we talked about in class, second part we have not yet talked about, so I'll go kind of quickly through the first part, maybe a little bit slower through the second part. So, first part, nuclear chemistry, right? All nuclear chemistry takes place in the nucleus, right? Stuff going on in the nucleus. So, this is a nucleus of lithium. We know it is lithium because it has 3 protons and because it has 4 neutrons and 6.94. The information for lithium, we can draw the nucleus of any element from its information on the periodic table. Now, in the nucleus of lithium, there are 2 forces at work. One is the electromagnetic force, and that is driving the protons apart because the protons are positive, right? Positive protons and positive things are driven apart by the electromagnetic force. And the other force that's going on in the nucleus is called the strong force, and that has to hold the nucleus together. Now, if the electromagnetic force and the strong force are both at work and the nucleus does not fly apart all the time, that means the strong force usually wins. The strong force is usually stronger than the electromagnetic force holding the nuclei together. All right. It's when the strong force is not as strong as the electromagnetic force that we get some kind of radiation, some kind of issue, some kind of problem going on. All right, just a note on isotope notation, if you're unfamiliar with it up until now. This is what that lithium nucleus looks like in isotope notation that has 3 protons, the number of protons goes in the bottom, and 7 particles total, and that total number of particles goes in the top. That number on the bottom really isn't the number of protons, it's really the nuclear charge. So the nuclear charge is 3, and that number on the top is really the mass number, but it corresponds to the total number of particles on the top. Lithium, because the atomic mass is a decimal, has 2 different isotopes. 2 main different isotopes, and these are the 2 different main isotopes, lithium-7 and lithium-6. Sometimes you'll see this written as lithium, a little dash, and then a 7. You know that it's lithium, you know that it has 3 on the bottom. This just indicates the number on the top. So this is lithium-7, and this one would be lithium-6. Another way to write it. Lithium-7, lithium-6. We also talked about 3 different isotopes of hydrogen, and they actually have different names. This is just regular hydrogen, just 1 and 1, because there's only 1 particle and 1 proton. This one's 1 and 2. This one's called deuterium, and this one's called tritium. And deuterium actually is given a D symbol for its actual, when it's like in a compound, you can make water with deuterium, and actually have Ds over there, versus water with regular hydrogens. And so if you see that later on, that is deuterium. Tritium, as far as I know, doesn't have a symbol of its own. I've never seen tritium with a T, but whatever. All right, so we've already talked about this. We'll continue on. So here are the different kinds of radiation that we need to know. 3 different kinds that we're going to talk about. There's like 8 or 9 different kinds, but the 3 kinds we're going to talk about are alpha, beta, and gamma. Alpha radiation occurs because there's simply too many particles in the nucleus, right? The nucleus has too many particles to be stable, and that causes the nucleus to spit out some particles. It loses 2 protons and 2 neutrons to end with a 0, so that's 2 neutrons. And those particles fly out as the particle, and that's what the particle looks like in isotope notation. So here's an example of alpha decay. A uranium nucleus, which is extremely large, right, too large to be stable, spits out a helium nucleus, which is an alpha particle, and what's left over is a thorium nucleus. It's thorium because it has only 90 protons left. So this, in this reaction right here, this is called the parent isotope. This is the radioactive particle, and this is called the daughter isotope. What's left over after radiation has occurred is called the daughter isotope. So we got uranium, and it spits out a helium nucleus, and the daughter isotope is remaining left over. So that's alpha decay. Alpha decay, again, too many particles, so it spits out some particles to alleviate that stress, and there's an example. Second type of radiation is called beta decay. Second type of radiation is called beta decay. That occurs not because there's too many particles, but because there are too many neutrons in the nucleus. There's an imbalance between neutrons and protons. So how the nucleus changes is a neutron turns into a proton. So essentially, we lose 1 neutron and gain 1 proton. It's not like the neutron leaves and the proton arrives, it's just a neutron turns into a proton. And when that happens, an electron is also created, an electron is also produced. So the radioactive particle is just that electron. Right, the radioactive particle is just that electron. And here's it written in isotope notation. So here is an example of beta decay. Carbon-14 is unstable because it has too many neutrons. Excuse me. Too many neutrons, and so it's going to undergo beta decay and become nitrogen-14. Sorry, there's a hair in my mouth. There we go, got it. All right, so carbon-14 undergoes beta decay, becomes nitrogen-14. These things, if you're having trouble looking at the numbers on here, on the top and the bottom, these numbers need to add up, as if there was an equal sign kind of right here in the arrow. So the arrow sign, or the arrow is an equal, and then this plus is a plus. So 7 plus -1 is equal to 6. 14 plus 0 is equal to 14. Also works up here. 90 plus 2 is equal to 92. 234 plus 4 is equal to 238. Okay, so that's alpha and beta decay. The third type of radiation is called gamma decay, and that occurs simply because the nucleus has too much energy. So too much energy going on in the nucleus, and it just loses a photon, which is a packet of pure energy. So that photon really doesn't have any particles in it. It's not electrons or protons or neutrons. It is just a photon, which is just a packet of energy, and that's how we write a photon in isotope notation. And so here's an example of a radioactive sentence that has gamma radiation in it. Now here's thorium, that same thorium that we had up here. When something undergoes decay, a byproduct of that decay is energy. So this thorium nucleus is going to be highly energized because it underwent alpha decay, because of the mass defect, which we'll talk about in just a little bit. So that thorium nucleus, we draw it as having too much energy by putting this asterisk right here, this little asterisk that we have right there. That just means that that thorium nucleus has an excess of energy. Now, it's still unstable because it has too many protons and actually too many neutrons. So this thorium nucleus could undergo any type of decay, alpha, beta, or gamma. We're just happening to show the gamma decay in this example. So it undergoes gamma decay, and it spits out a gamma particle, and that's how we write gamma particle in isotope notation. And also and so what's left over is just the same thorium nucleus. It didn't lose any protons or neutrons or electrons. It just no longer has the asterisk right there. It just is now slightly less energetic. So that is the 3 types of radiation that we need to know. This is technically beta negative or beta minus decay. There's also beta positive decay, in which it has too many protons, and then a proton turns into a neutron and also spits out a positron. Positrons are positively charged electrons, but beta negative decay is much more common, and we don't need to worry about beta positive, or beta negative rather. Nope, sorry, beta positive. We don't need to worry about beta positive. Okay, this next thing is a graphic representing how the 3 different types of radiation would react to a magnetic field. We can actually separate the different kinds of radiation by a magnetic field because the different kinds of radiation have different charges. An alpha particle is 2 protons and 2 neutrons, so it is positively charged. A beta particle is just an electron, so it's negatively charged, and a gamma particle is nothing more than just a photon, so it has no charge at all. They range in charge and in size. The alpha particle is heavy, the beta particle is much lighter, and the gamma particle is, there's the bell. The gamma particle is infinitesimally light. It essentially has no mass, right? It still is affected by gravity, because gravity is relative and blah, 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 but it essentially has no mass. So we can separate these out by their charges, because if we subject all 3 of them to a magnetic field, the alpha particle is going to go away from the positive and toward the negative plate, because it itself is positive, so it's going to be attracted to the negative. The beta particle is going to curve toward the positive plate, because it itself is negative, and the gamma particle is just going to go straight through, unaffected by the magnetic field, because it doesn't have any charge. So, like a block of uranium, a piece of uranium is going to have all 3 particles coming out because it's going to be undergoing all 3 different kinds of decay. And this is technically beta negative coming out there. So I just encased it in a block of lead because lead will absorb all 3 different kinds of radiation. So we're just spitting it out in one direction. Okay, so this is an example of how the 3 different kinds of radiation react to a magnetic field. All right. Next thing we want to talk about here is what can stop the 3 different kinds of radiation. So what they can be stopped by. So that same piece of uranium inside there spitting out both alpha, beta, and gamma particles, in the case of that block of lead. So we have all 3 different kinds, and this one is mostly not due to their charge, but due to their size. They can be stopped by different materials. Alpha particles are the biggest, right? Alpha particles are those 2 protons and 2 neutrons, so they're the largest of the particles, and so they can be stopped by the easiest stuff. They're the easiest to stop. So just regular paper can stop alpha particles. They are easily stopped by paper, which means that if you're exposed to this radiation, alpha particles are going to hit the surface of your skin and stop, and they're just going to do damage on the surface of your skin. Beta particles, however, are smaller. Beta particles are electrons. They're quite a bit smaller than these particles, and so they can go straight through paper, and they're stopped by foil, by metal foil, having to do with the density of the metal foil and the deal cause electrons and other stuff that we don't need to worry about right now. So metal foil stops beta particles. And then lead or concrete can stop gamma particles. Gamma particles are just those photons. So we have a gamma particle, that's just a dot, right? It's just really, really tiny dot, very high energy. It's also going the speed of light, so it's much harder to stop. So it can go straight through paper and metal foil, and it's stopped by many feet of lead or concrete before you're going to stop most of the gamma radiation. So it can go through a lot of stuff, and it's only stopped by lead or concrete or other materials if you stretch them out enough. Lead and concrete are just kind of the ones that are used as a go-to because lead's very dense and concrete's pretty dense as well. So if you're underground under many feet of concrete, you can survive nuclear fallout because all that stuff is going to be stopped. All that radiation type stuff is going to be stopped. So here's what can stop that of 3 different kinds of radiation. So I think it's kind of ironic that we have basically concrete, which is rock, and then we have paper, and then we have metal foil, which essentially is scissors. We have rock, paper, and scissors, but yeah, whatever. All right, so the next thing we'll talk about is fission. Another nuclear reaction, other than alpha, beta, and gamma, is fission. So fission is when a large nucleus splits into 2 smaller nuclei. Usually this is set off by a free neutron hitting that large nucleus, and usually it releases 3 more neutrons. It doesn't have to happen, but it does most of the time. So a neutron, we usually kick a neutron into a uranium nucleus, a free neutron from somewhere, we don't need where, and that energizes the nucleus, makes it unstable, and causes it to split apart into two smaller nuclei. Now, all these numbers have to add up. So we had 238 plus 1 more, so we had 239 over here, right? So we had 239 for total number of particles. There should still be 239 on this side. Should still be 239. I think I have 1 extra particle though. 15, no, it might actually be right. So anyway, the number of protons has to equal the same. So 45 plus 47 should equal 92. And then 115 plus 121 plus 3 should equal 239 because there's 1 extra neutron. I think it does. So anyway, it splits into 2 smaller nuclei and also releases 3 free neutrons and also releases a crap ton of energy, a huge amount of energy. Now these 3 free neutrons can then go on and do the same thing to other uranium. So if you have a sample of uranium, this can continue and continue and continue on, creating a chain reaction. Now, if that sample of uranium is large enough, big enough and dense enough in what we call a critical mass, this can cause an ever-increasing chain reaction that will eventually result in an explosion. If it's small enough, then it's just going to cause a chain reaction and enough of the neutrons are going to escape that it's not going to cause an explosion. It's called a subcritical mass. So where this occurs in nuclear reactors that use uranium and also in nuclear bombs and nuclear fission bombs like the ones we dropped on Japan in World War II. We're the only country to ever drop nuclear explosives on anybody in war. Yay, go us, USA, USA. Woo. All right, fusion, which is the opposite kind of a fission, is 2 smaller nuclei smashing together to form a larger nucleus. So like 2 particles of hydrogen, these are both deuterium because they both have 2s, smashing together to form helium. When this happens, when they fuse together, they also release a giant amount of energy. Now this has to happen at extremely high temperatures. Like this is what occurs in the core of the sun to fuse hydrogen into helium that actually fuels the sun and gives us all the energy almost all the energy we have here on the Earth. So these 2 things fuse together and produce helium. They have to be going so incredibly fast, they have to be so incredibly hot because the repulsion, the electromagnetic repulsion, kicks in long before they get anywhere near each other. So as these 2 get closer and closer together, they're feeling more and more repulsion. They're slowing down and slowing down. And it's only after they essentially touch that the 2 fuse together into the new nucleus. Once they actually touch and fuse together, they are stuck together because of strong force interactions, but they have to be going really fast before that happens. So that, yes, occurs in the cores of stars, and that's where all of our elements are forged, is in the cores of stars. Okay, so both fission, fusion, and all the radioactive types of radiation have what's called a mass defect. And in all of those different kinds of radiation, we have this thing where some of the mass is actually lost during that reaction. Some of the mass is actually lost. If you looked at fission, and you gather together all the products over here, they would actually weigh slightly less than the starting product. Some of the mass would actually appear to be gone. And that, from the mass that disappears, that's where we get the energy. The energy comes from that mass that has disappeared. It's not really gone, it hasn't gone anywhere, it simply has been changed right into pure energy itself. And it's the source of all energy for the radioactive processes, and the reason why there's so much energy is because of this equation right here. The E equals mc squared. Really, this is relating the mass of an object to its energy if all of the mass was actually turned into energy. And that c is the speed of light, so that's 2.998 times 10 to the 8 meters per second. So even if you take a really tiny, tiny mass, you're multiplying it by a very, very large number squared, so the amount of energy is going to be very, very, very large. If you took this pen and you changed the entire pen into pure energy, you would have an explosion that took out most of Southern California. So don't do it. because I live here and I like it here and such. Wait for me to move away. Then you can vaporize California. I don't care after that. All right. So last thing we need to talk about in here is called Half-Life. Last thing we need to talk about in here is called Half-Life. Apart from being a very enjoyable video game series and franchise that takes way too long for the sequels to be released, Half-Life is defined as the amount of time it takes for half of the remaining sample to decay. All nuclear reactions occur by first-order kinetics, meaning it matters how much there is of the sample for how fast the sample is going to go. Very large concentration, high concentration of material means it's going to go faster, lower concentration of material means it's going to go slower, and the smaller and smaller amount it has, it is going to be slower and slower. So if you have, let's say, a sample of sulfur-35, sulfur-35 has too many neutrons, so it's going to undergo beta decay and spin an electron to become chlorine-35. The half-life for this is 90 days. Meaning, if you have a 100-gram sample of sulfur-35, after 90 days, that sample is going to be 50 grams of sulfur and 50 grams of chlorine. Now, it's not going to be exactly half and half. It's not like you can come back to this sample in 90 days and break it in half and be like, oh, I now have 50 grams of sulfur on one side and 50 grams of chlorine on the other side. It's going to be interspersed. It's going to be interspersed all throughout. It's randomly going to be all the way through. It's almost completely homogenized. So yeah, it's not like you're going to be able to get the two back away from each other. So 50% of it will be sulfur and 50% of it will be chlorine. After another 90 days, only 25 grams will of sulfur will remain because it's half of what was remaining. Not the other half is not going to go. It's going to be half of what the remaining sample was. So 100 went down to 50, then after 90 days it went down to 25. After another 90 days, it's going to go down to half of what that is remaining, so 12.5 grams. And then the other percentage, 87.5% or 87.5 grams, will be that chlorine-35. So each half-life, as each half-life goes by, half of the remaining sample decays. So 100 became 50, became 25, became 12.5. Now the types of problems that you could get using this are problems like this one. So how much of a 896 gram sample of sulfur-35 will remain after 540 days? And to do this problem, we're going to have to give you the half-life. So let's say the T1 half, like we set up here, is 90 days. So here's how I would solve this problem. You don't have to use this method. There's equations to use this to do this, but this is how I would solve it. So I would first set up my table right here with sample, number of half-lives, and time, how much sample I had left. So to begin, I started with 896 grams of the sample. That was from the problem, 896 grams. And that's at time 0, after 0 half-lives have gone by. Then I would say, okay, 1 half-life, that means 90 days have gone by, because that's my T1 half, and half of this sample is going to decay. So that means that I'm going to divide whatever that number is by half. So half of 896 is 448. And then after 2 half-lives go by, that's 180 days, because it's 2 times 90. And then we are going to have half of that sample decay again. So half of this goes away, so half of it, 448, is 224, and after 3 half-lives, 270 days, 112 grams remain, 4 half-lives, 56 grams remain, 5 half-lives, 28 grams remain, and 6 half-lives, 14 grams remain. So it says how many will remain after 540 days, so we see 6 half-lives is 540 days, and that's 14 grams that will remain. So for each of the problems that's on the review and will be on the final, you can solve it using this, and it'll be somewhere in here that you can, yeah, it may not be an exact multiple and exactly cut in half, but in multiple choice, the number will be somewhere nearby. It'll be nearby to a whole number of half-lives. There is an equation that you can use that determines how many days have gone by based on the concentration and the time, and there's a logarithmic thing, but we're not going to learn it this year. We'll learn it next year in AP. So that is basically all that you need to know on nuclear chemistry, and you should know everything you need to know for the review and for the midterm. No, final, not midterm.